Welcome. We're going to talk about Python memory for speed and efficiency in some pretty interesting ways here. So what we're going to do is we're going to start by looking at just some of the ways in which Python memory works. I find that Python memory is a bit of a black art, like mysterious wizard type of black art. Well, maybe not that kind of wizard, more like this kind of wizard, a coding wizard. But really, people don't speak the same level and depth about Python memory as they do in languages like C++ or Java or .NET. All those ecosystems, they obsess about the little details. And while I'm really glad we don't obsess about the details of Python memory, I do think knowing a little bit more than is frequently spoken about is really useful. So what we're going to do is we're going to fly through some concepts to give you a quick overview of how Python memory works. And then we're going to see a little bit of code first to explore that memory, but then later to actually things we can do concretely to improve it. And let me just give you like the far end of the spectrum of where people are doing crazy stuff with memory. Instagram turned off the garbage collector on Python and got a 10 to 15% speed and memory usage improvement. They turned off the garbage collector and they saved memory. How weird is that? So there's these knobs that we can turn in the Python space that often are not spoken about. You don't need to go turn them. You probably shouldn't fiddle with them a lot of times, but knowing they're there and knowing some coding patterns that allow you to write code way more efficiently just is really, really powerful. And it's surprising, I think you'll see. And what surprised me the most about diving into this, I expected to understand Python memory better and therefore writing code that used less memory. What I didn't expect is that, say, the Talk Python training website, for example, is now, quick math, about 15% faster, somewhere like in that scale, faster because I turned some of these knobs. So really, really interesting things that we can do to make our code not just use less memory, but actually be faster. So I think that's the real win we'll see, but also the understanding. So let's start at the beginning. I know some of you have done C. We're going to talk about C. When we say, hey, I write some Python code and I ran it, it runs on what? On CPython. And CPython is written in primarily C. Some of the standard library is Python, but a lot of it is C. Now, we're going to really quickly look at some C code. You don't need to understand C. It doesn't really matter, but I'll just talk you through it. So let's look at an example. Does C and C++ have pointers? Well, sure it does. These person star P1 and person star P2, those stars mean pointer, not actual value. And notice where it says P1 dash greater than ID, follow the pointer to where the thing is, and then look at the value. So if you look at the actual values of P1 and P2, they're memory addresses. They're not the actual person. They just say, if you go over to that place in memory, and however big a person happens to be, you'll find a person object called P1 there, or referred to by P1. So out here in memory, these things point at this. Now, there's really important questions around this memory. Who owns it? Well, in C++, it could be the person who created it, or they could have handed it off, or they could have created a construct like a smart pointer. There's all sorts of things. It's not super clear. How long will they stick around? Well, till someone deletes it. Could be the owner, could be someone else, who knows. If we forget to delete it, that's kind of bad. We have a memory leak. If we free them too soon, it's really bad. We have a crash or security vulnerability or something. So thinking about memory, you see, these are important questions to answer, and you're always obsessed about them. What about Python? We got pointers in Python? No, of course we don't have pointers in Python. That's ridiculous. So here we have P1, they're a person, P2, they're a person. You see we have a dot, no arrow types things, so no pointers. But if you print out P1 and you print out P2, you get something that looks suspiciously like a memory address out on the heap. Wait a minute, what's going on here? And you can actually ask for the ID of them in CPython. That'll give you the base 10 address in memory. Wait a minute. In fact, yes, out in memory on the heap, just like C++, we have these pointers. Other questions, who owns these objects? Well, it's much simpler. Python, the community, all the variables that might work with it kind of as a group own it. And when no variables are paying attention to it anymore, then the thing can be cleaned up. There's two ways, not just one, there's actually two ways in which it can get cleaned up in Python. How long do they stick around? Well, usually till all the variables are done pointing at them. Unless they're complicated, then it takes longer, maybe at the end of the program, as we'll see. So if you really want to understand Python memory, you have to decide, do you want to take the red pill and peel back the covers and see the truth? Or do you want to take the blue pill, as Neo is being offered here, as Morpheus is offering him, to kind of put the facade back up and pretend it's all simple and clean. We're going to take the red pill. And when you take that, you can look at code like this. Age equals 4,200. So simple. We don't have to say the type. It's not int age. It's not allocation of a 42. Just boom. Couldn't be simpler. Unless you look at what's actually happening down in the CPython runtime at bit.ly/cpython long. Awesome. All this code is now on GitHub, so it's super accessible. Here's what happens when you create a large number in Python. So you can see it's calling a function that returns a pi object pointer, and somewhere there's like a pi long new. Whoa. What's going on here? Yeah, all of these things are pointers. In fact, Python has more pointers than C, because C at least has the option for like numbers on the stack and stuff. Even numbers in Python are pointers. So yeah. Bring me some PyCharm. There we go. All right. So I first want to just explore, like, what is the size of a variable? Like, how much memory? I'm gonna give you a sense of how much memory does a standard Python thing, how much memory does that use? Okay. So how about a number? For those of you who have worked in lower level languages, you would know that numbers like 4 can be represented as, I guess, even 1 byte, but typically they're either shorts or integers or longs, which would be 2, 4, 2, 4, or 8 bytes, I believe. It's been a long time since I've done that. And that's how many bytes they take. They take 2, 4, or 8, depending on the variable you get. So let's go over here and we can print sys.getSize of the number 4. Okay, if we run that, what answer do we get? The size of the number 4 is 28 bytes, because everything in Python is one of these pi object derived things, even numbers. So there's all this information on like how many variables are pointing at the 4. What type is it anyway? What other functions does it have on it, and so on. So there's more overhead, but there's also more richness. All right, well, that's interesting. All right, so a letter, I mean, in C, that would be that's an ASCII probably, so 1 byte. So you'll see it's about 1 byte or 50 times larger than that, because it's a string. In Python, we don't have characters and then strings like we do in other languages. We just have strings that happen to have one thing in them. So that's what that size is. We'll say get size of, well, what if we want all the letters? I could type all of them out, or I could just multiply a string by 26 and get 26 A's, which means the same thing. And you get an interesting thing here that the initial string class is 26 bytes, or sorry, 49 bytes. But then every other character is just 1 more byte. So 49 plus 26 is 75. So there's kind of this growth that doesn't really count against it very much. How about a list? This gets a little bit interesting, and then we're going to move on to writing a little bit more code here around allocation and deallocation. So let's go and say sys.getSize of a list. A list, it's like a string, 56. What about a list like this? That list. It's 152. Now, if you think about this for a minute, I just told you that numbers were 28 bytes. There's 10 numbers in here, so that's at least 280 bytes, and something is going on here that is wonky. So when you're exploring memory, you have this get size of that kind of tells you stuff, but it only tells you the immediate object that you're working with. But that object, like this one, points off potentially to other objects, which themselves could point off to other objects, and those are not measured. So all we're really measuring is how much does it take to store 10 pointers, but those things could point at who knows what. So there's another little library that I put in here that has a get full size of that basically does recursive traversal of the object graph in memory, calling get size of on every single thing. So if we run this again, but with this better version, size util.get the full size of, then you can get to the actual size of these. All right, so super interesting. I think it's probably enough given the time that we got to work on this, but just gives you a sense of like, what is the size of a thing? It's not just, a couple of bytes for a letter or something. Normally it doesn't matter, but knowing these things certainly is important. All right, let's look back over here. Now, there's 2 interesting aspects of Python memory. everyone focuses on the cleanup side. They say, okay, well, does it use reference counting? Does it use garbage collection? Does it smart pointer? Like, what does it do? Well, that's way down the line. At the beginning, the question is, how do I get memory? And you might think, oh, it's super simple, Michael. We have hardware like RAM in our computer. We have an operating system like Mac OS that I'm on. It manages virtual memory to isolate memory, and that's dedicated to a process. It's written in C, so we have malloc. Boom. We malloc our bytes and off we go. Python needs to create one of those letters. It's 28 bytes or whatever it was, or 56 bytes, 49 bytes. It's going to create one of these mallocs for that memory, and then off it goes. No. There's way more to it. There's all sorts of things about reusing certain parts of memory and grouping memory together based on like the sizes for avoiding memory fragmentation and so on. So in fact, this is the layer of what happens. But if you keep going, there's a special dedicated allocator inside of Python called pymalloc, the pymem API. And then on top of this, when you have small objects, which means an object that is less than 512 bytes, which might not sound that common, but remember, most things are some object that contain pointers to other objects, like a dictionary contains a bunch of items that point off to other places. All of those things would probably count as small objects because that's less than 512 bytes. All right, so this is the whole workflow in Python. And if you go and look at the CPython source code, you're going to see something that may blow your mind. It blew mine completely. There's an ASCII diagram in the source code documentation. Like, this is the comment of the allocation function. And it had, look at this. It has a ASCII diagram like, oh, here's the object specific memory and the core memory and the Py object allocator and so on. So really, really interesting stuff you can dive into. I'm going to just skip ahead real quick because we don't necessarily need to like jump too much into detail, but quick summary here. Python uses 3 structures, which you can look further into. It uses blocks, which hold objects of the same size, not necessarily the same type, but the same size. So here's a block that holds everything that's 8 bytes or smaller, and it could just waste a little space. And then those blocks are organized into pools, which are larger groups of memory that fit better in the operating system, and those pools are managed by arenas. So there's like these 3 levels of management there. Okay, so we get something allocated using this mechanism, and we want to know, well, I told you all of these objects, these Py object pointers that we allocated, they were larger than maybe we expected at the beginning. And the reason they're larger is they carry extra information. What type is this thing? What additional information on it? And importantly, it's obref CNT, right? Object reference count. And it has a very weird data type of pi s size of t. Think of that as like a long on a 64-bit system or an int on a 32-bit system or something like that. So we'll say long. And this is just a number that says how many variables point at me. If that number ever goes to 0, boom, that thing's cleaned up. That's as simple as it gets in Python. We have these pointers, you point at them. As long as there's something pointing at it, it sticks around. As soon as that gets to 0, as soon as no longer variables point at it, they go away. And that would be really simple if that was the end of the story. It's not quite, as we'll see. Okay, so let's go look at this reference counting real quick. Let's put this away. Hide them away. So yeah, you can check that code out later. So I got 2 versions. And I've got this really unfortunate class here that I've created called Doomed. Doomed is a class whose sole purpose is to do print statements around its life cycle. When it gets created, it says, hey, I'm created. I live at this address. When you ask what it is, it jumps out like, hey, I'm this thing at this address. And then del is like the finalizer, the destructor, if you will, of classes in Python. It has nothing to do with the del keyword. It's just when it gets cleaned up. And this is like right its last moment before it's a goner. All right. So over here, let me set this to run. What we can do is we can come and create one of these doomed objects, and we can, I wrote this little utility to get the reference count. You can check it out in the code. It's not really super interesting, but it's kind of interesting. Given one of these IDs, one of these memory addresses, without holding on to the object, tell me how many reference counter, how many pointers, what is its reference count? How many pointers point at it, right? Because if I created a variable and then ask questions about it, well, then that's like quantum mechanics. I've changed it by observing it, sort of thing, right? I need to make a way where I can ask questions about that object without actually referring to it. So what we're going to do is we're going to create one of these, and then we're going to say how many things point at that thing that got created out in memory on the heap. Then we're going to create another variable here by assigning v1 to v2 and ask, now how many pointers does it have? Then we're going to say, well, you don't point at, actually we could swap these even. It could be a 1, then a 2. It doesn't matter, but we just take away one variable from it. This should go down. Take away one more. It should go away. Let's see that that's the case. Perfect. So check this out. We created our doomed object. In the beginning, the reference count was 1. That was right here when we had our first v1 is pointing at it. Now v1 and v2 pointing at it, so that's 2. And then v1 was gone, so only v2 is left. And then as soon as we wrote line 20, before the print statement, that reference count hit 0. Python noticed that and deleted it. Boom. See, Python memory, it's simple. Yeah. Except. When does reference counting break? It breaks when there are cycles. If I have one object that points to another, but then that other object points back to the first, you can end up in some really tricky situations. Think of like spouses in some sort of relationship or something like that. And if we just quickly look over here at this one, we have the same objects, but now we have 2 of them, and they have these friends list here. So for the friends, we're going to do the same thing. We're going to get their IDs, then I'm going to set them to none. And then, well, because the only 2 variables we have are v1 and 2, this should wipe them away. Yeah. So let's run it, see what happens. All right, cool. So created our 2 objects. Reference counts are 2 because we have v1 points at this thing, but also v2 has friends, which points at that. So that's 2, and vice versa, also 2. We go down here and wipe it away. And now they're 1. And now what? We have no more variables that point at them. There's no way to address them or to find them or to know about them or to affect them. And yet their reference count is 1. That's weird. What's going on here? And notice we get all the way to the end of the method and the whole program ends. And then on shutdown, they get cleaned up. So that's the cycle. They didn't get cleaned up. So what happens? Well, Python also has a secondary garbage collector built into it. And if we do enough memory allocation, like here, we're going to create a list, which has a bunch of strings, and then put that into a list. If we do that, notice after we stop pointing at it, they were garbage. Eventually, specifically when we allocated 700 of these, exactly, Python found that those were garbage and cleaned them up, and then the reference count goes to 0. So the way Python memory cleanup works is we have this reference counting, which is super clean, except for when it's not. And we have this backup garbage collector. So let's look at that real quick, and then we'll do some optimization around these things. So there's this generational garbage collector, just like .NET and Java have, and with the generations and everything, just doesn't compact. And as objects survive garbage collections, they get older in these generations. The important thing to know, though, is in Python, garbage collection only applies to container objects, lists, dictionaries, classes, sets, tuples, things that could potentially create a cycle. A string can never create a cycle. A number can never create a cycle. So they're not part of this garbage collected world. When does it run? Well, you can call gc.getThreshold, and it'll return 3 numbers that are confusing. They're confusing because their units are not the same. The first number says that we're going to run a garbage collection for the newer objects, Gen 0, after the allocations of a collection object happen 700 times more than deallocations of those collection objects. Exactly 700. That's what that number returns. Second one is for every time you run Gen 0 collections, every 10 times you do that, do a Gen 1. And then the last number is every time you run a Gen 1 collection, every 10 of those, do a Gen 2. So it's a 110-1 type of ratio. All right. So you can also modify this and you say gc.setThreshold. And this is really interesting. Like I was talking in my little table, I guess you call it here. Over at Talk Python Training, we have a ton of stuff that we want to generate a sitemap around, like transcripts and courses and like thousands of records out of the database. When we rendered that page, I could check, and we did 77 garbage collections on the one page request, every request. That's insane. And that's because we were returning thousands of records, and every 700 as they came back would trigger a new collection over and over. So in production, we actually run this at 50,000, 10, 10, and we got a 10% speed up in like our unit tests and our integration tests and just across the board. And basically no memory growth. It was like 20 megabytes when it's normally 2 gigs on the server. I mean, it was right at the margin. So something you can play with. This is one of those knobs you can turn. All right. Let's go look at functions. This may be the last thing we have time to look at, but this is another really interesting concrete thing that you can play with. All right, let's put this stuff away. Down here. Yes. So let's look at a standard data processing pipeline. You don't have to be a data scientist for this to be interesting, but I think it's probably the most important use case. There's a data science memory profiler, like memory profiler that Corey mentioned at the beginning, that's really interesting, but focus more on the data science thing. And the guy who created that wrote this cool blog post called something like clingy functions or something like that. So here's one of those. So I've got this, let's go, yeah, this one. We'll run our main. So here's the idea. We're going to load up some data, which is like, get me a big list of data. I'll store that in a variable called original. This is what I consider good code, except for this bit here with the semicolon. That's just to get an output. Forget that. Then I'm going to take that data. I'm going to filter it in this functional way and return a new list of filtered data. So in this case, what we want to do with like filtered data is say we're going to just return all the odd numbers. Okay. And for the load data, we're going to generate the number between 1,000 and 10,000 a million times. Okay. And then at the end, we're going to scale the data that was filtered by my favorite number, a small version of E, 2.718. And then we're just going to print out the numbers and see how much memory that took. Cool. Let's run that. So here it goes. It takes a moment. It says, well, how much memory do we use? We use 273 megabytes. That's how much memory process growth happened from like the first line to the last line, basically. 273 lines. Well, some languages like .NET have a debug version for working with it and a production release version. C++ has this as well. And it does different stuff at runtime, like the compiler is more optimizing and it does other things. Like one of the things it would say potentially is like, after this line, original is not used anymore than this function, so we can effectively clean it up and throw it away. Python doesn't work like that. Python says you had a variable in this function. And so until you're done with that function, that variable is going to be hanging around. All right. And what that means here is we load up this original data and then we create the filtered, but we still have original around and we're not ever going to use it again, but we just happen to be, haven't done anything. Like if I wrote code like this, original equals none, PyCharm is going to grade out and say, you should never do this. This has no effect. Oh, it has an effect. It has a big effect, as we'll see. But because we're not doing that, it builds up. We're going to hold original, filtered, and scaled all in memory until the end of the function. And all we care about is the final bit. So let's write some crappy code, something that somebody would look at and go, you know what? You're not that great of a programmer. You need to name these better. So what if we just called this data? And over here we had data. And then the next step, now the data looks like this. And the next step, data looks like that. And this one, I'm going to rename that so I don't have to type it. There, data, 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 data. Like this is not good code, but watch. Oh, look, it uses 100 megs less. That's crazy, right? Why is it using 100 megs less memory? It's using 100 megs less memory because it's effectively doing what the optimizing compilers of C++ and C# and so on do. They say, you know what, on this line, we're done with the first version of data. Now we have a new version of data. And then after this one, on this line, we're done with the filtered version of data. Now we have the scaled version of data. Amazing, right? Let me show you one more though. I know I've got like 14 seconds. It won't take long. So we could go over here and we could rewrite, actually, I'll just rewrite this one here. We could rewrite this code. Let's go to this load data. And let me see that square bracket? Let me type parenthesis like this. And let's go to this filter data. Let me take that and type parenthesis, rerun it. Now we dropped 110 megs. Why do we lose so much memory? Like, what is going on here? These become generators with parentheses, and they become lists with square brackets. If they're generators, what that means is they only load one of them into memory at a time. So instead of loading all of the data, the entire loaded data, and then all the filtered data, we took, well, give me one loaded data. And then let's pull through that and just get one of the filtered data and pass that off to scale and hold on to it. So this combination of using generators, maybe they look like this, maybe they look like for n in data. It could be like this. You could say yield n. You could write it either way. It doesn't really matter. Like, there's both versions. They all come out with exactly the same output, basically, right? But however you come up with a generator, whether it's the generator expression or a proper generator, they're dramatically better for not loading all the data into memory. All right, well, hopefully that gives you all some things to think about, how memory works. You can see that we can do this wonky naming thing here where we don't hold on to the intermediate data by just reusing the variable name. Definitely put a comment on there. Or we can use generators in the case where it makes sense and only load one of them into memory at a time. All of these are great options. You can see they also work together in combination. All right, real quickly, if you want to find out more than that, I have a whole class on this about Python memory management. It's like 4 or 5 hours over there at talkpython.fm/mem. You can check that out. If you don't listen to the Talk Python Me podcast, please check that out as well. We do all sorts of stuff. For example, I had a whole episode about Phil and the guy who wrote this article. As you can see, apparently that was episode 274. So thank you for your time and your interest and attention.